Well, hello everybody, welcome. Today we are going to derive the formula for this distance Lx. This is the moment distribution, this is the load diagram, this is the shear diagram, and this is the moment diagram. Most of the time you will encounter this problem here. You need to solve the value of this distance here so that you can calculate the area, this area here and this area here. Supposed to be numbered, but anyway, um, to derive this formula I extracted this portion here and put it over here so you can see better, right? As you can see, there are two triangles in here. It's triangle 1 and triangle 2. We need to derive the formula for this distance Lx so that you can use it like very quickly. Alright, so to solve the problem is to, by similar triangle, you have to equate both triangles. Triangle 1 is equal to triangle 2. Alright, so triangle 1 is equal to triangle 2. In triangle 1, Lx over R1 is equal to the triangle 2, which is L minus Lx over R2. Alright, that's the first equation you're gonna have. Alright, the Lx over R1 is equal to L minus Lx over R2. The R1 and R2 are the shear for that portion of the beam. The R1 is the reaction RA, the A here, reaction RA. And the R2 is the shear below the shear line, which is the sum of the reaction RA minus the downward force of the uniformly distributed load. Alright, and then you have now this equation by cross multiplying this equation here, right? By cross multiplying this equation, the R2 here will be multiplied by Lx, and the R1 will be multiplied by L minus Lx. So we have this now. Lx times R2 is equal to R1 multiplied by L minus Lx. And then you multiply this portion of the equation. R1 times L is minus Lx minus minus Lx multiplied by R1. You have Lx R1, and on the other side of the equation you have Lx R2. Okay, that's the first two lines of the equation. Now the result of this multiplication here, you have R1 times L minus Lx minus R, and then transpose this value here minus Lx to the other side of this equation here. So you have Lx R2 plus Lx R1 is equal the R1L will remain in this side of the equation. So you have now the equation Lx R2 plus Lx R1 is equal to R1 times L. Now next is the collecting like terms. The the Lx here will be factored out from the R1 and R2, so that you have this result, Lx times R1 plus R2. R1 and plus 2 is inside this parenthesis here, right? Because you factored out the L with X. And the next, simplifying the equation now, the Lx is equal to R1 times L, bringing down this R1 plus R2 under RL. You have the result of Lx is equal to RL, R1 times L divided by R1 plus 2. So now this is the final equation, how to solve the value of Lx. Final equation is Lx is equal to R1 times L divided by R1 plus R2. And as I said, the R1 here is the reaction RA in the moment distribution. The reaction RA right there in the shear, and R2 is the sum of the positive and negative moment. This is the moment around here, this point here. The area 1 is the moment here. If you solve the area of this, but there is a negative moment right here, so you sum this moment, the positive and negative moment. Sometimes becomes positive, sometimes it becomes negative. When it is positive moment, it is above this moment line, okay, and below that these are the negative moments. So now you can solve also the other triangle, the area of this other triangle, the moment here, okay, minus this area here will become the shear at B. Alright, so now since you have this Lx formula, you can now substitute that value into L minus Lx, so that you get these distances here. In the same process right here, see the little triangle there? This is a really small distance here. So what I did, since it's very small distance between this, I just calculated the area 1 here, area 2, area 3 areas, alright, and then proceeded to the moment right here. There's no point of calculating this moment right here because the distance between is too small. The reason why I say that is because when you design this structure, you have to refer it to the moments around here. The moment here is used to design the reinforcement bar. Moment here is used to design also all the reinforcement bars are designed based on the specific location of moments. And since the moment here, you're not gonna cut the bar here. It's the same bar will go here, right? So it's a very small distance. So I go after the moment right here. All right. So I'm not gonna discuss further for this the design and the shear moment diagram, because this topic is about the distance Lx, as I call it, is the most troublemaker distance in the shear diagram. Alright, there we go. There you have it. So again, you can apply that formula anywhere as long as you have these triangles right here. That formula is not applicable to this one here. Only this one here and this one, these two triangles, right? Solve this distance here using the formula. Using this formula, you can solve the distance here and also the distance there, right? Alright, Thanks for watching.